Let's go to the nitrogen oxides, which means we were dealing with the NOx emissions. Usually, the oxides of nitrogen are formed during the combustion process, namely as a result of chemical reaction of atoms, oxygen, and nitrogen. But in general, we will find out the results of the reaction between the oxygen and nitrogen will give us the nitric oxide and the nitrogen dioxide are two major oxides of nitrogen emit from the combustion system. And usually we have three categories, especially the amount of the nitric oxide basically is higher than the nitrogen dioxide in general. Then we will more focus on the formation of nitric oxides. And based on the discussions on the nitrogen oxides, we need to consider the three different categories of NO coming from the different mechanisms and reasons. Okay, the first one we call this is a thermal NO. Thermal NO basically is formed in the reaction zone of the, especially for the nitrogen and the oxygen, and they require under the high temperature in the reaction zone. The second, fuel NO, and we name it as a fuel NO, basically the N, the nitrogen atom in NO, basically coming from the fuel. Therefore, the fuel NO is formed by the released nitrogen of nitrogen content fuels at a competitively low temperature. And we mentioned the nitrogen containing fuel basically is belong to the coal, and sometimes you have a large amount of nitrogen from the petroleum. Then the third one is a small amount in the oil application. We call this as a plant NO. Arises principally from the reactions of fuel derived. Fuel derived means in the decomposition of a coal or petroleum, they will release some carbon hydrogen radical or carbon radicals, and those radicals will react with the nitrogen additionally. Then ultimately they will lead to the NO. In simple classification, you can understand thermal NO, the N and a nitrogen atom and oxygen atom come from the air, okay, from the nitrogen in the air, oxygen in the air. But for the fuel NO, the N comes from the fuel, then therefore we call this as a fuel NO, but O definitely come from the oxygen in the air. Plant NO, the N basically coming from the nitrogen in the air, but they require to react with the fuel intermediate, for example, the CH radical or C2 radical, as I mentioned. And here they have two important characteristics for these three kinds of NO. The major portion of NOx has been found to be the NO, okay? And the thermal NO is dominant source of NOx in most combustion devices because we always have a high temperature region, and usually you use air as the oxidizers, then you can have a big amount of the contribution coming from the thermal NO for the overall NO formation. But fuel NO is an important source for burning of crude oil and coal, okay? For natural gas, usually you don't need to consider the fuel NO. Now let's look at the thermal NO first. Since the thermal NO strongly, mainly depend on the temperature high, from the Jadovich studies, they proposed the Jadovich mechanism in 1946. And they tell you there is the three chemical reaction, including the forward and backward reaction, need to be considered as shown in this chart. And they list the relative rate constant and the temperature range for different chemical reactions. And you will find out there is the first one formula. the oxygen atom react with the nitrogen, they will form the NOx plus N, the nitrogen atom. In the presentation of rate constant, you can see there is a minus 38,000 divided by the temperature. 38,000 means the activation energy you may have for this reaction. When you compare the other chemical formula, and you will find out the 38,000, this value, this activation energy number is highest one compared with the other chemical formula, which means this the first chemical formula will be the dominant and rate determined, because there has this chemical reaction has the highest activation energy to be overcome. Then if you can observe enough energy, then all the chemical reaction will go through. Okay. And in this reaction, you can observe it, the range for the possible reactions through this chemical formula based on the 2000 to up to 5000 K, which means the 2000 K is very important temperature, the threshold for the temperature to produce to promote these chemical reactions. Therefore, always people use this temperature as the indication for the initiation of the NO formation. Okay, 2000 K. Here they mention the forward reaction of A. This reaction, the first reaction is rate determining. Okay, and they from the many literature, they find out reaction becomes important only in near stoichiometry and rich frames. Near stoichiometry means the temperature is pretty much high, but for the rich frames here, actually they partly caused by the prompt NO. Later on, I will explain it later. And they say the reason they they had a high temperature long enough to produce significant amount of NO. Okay, the near stoichiometry and a rich frame are possible burning process to produce a large amount of thermal NO. And the NO formation rate is much slower than the combustion rate. This is very, very important because we understand they require the formation of NO through the thermal mechanism. They require temperature high, means they need to wait for the heat of combustion release. Therefore, the NO formation for thermal NO, they need to wait the combustion process complete. Okay. Then they conclude the NO formation rate is much slower than the combustion rate, and most of the NO is formed after complete or combustion. Okay, therefore, by designating a post-flame zone, the NO formation process is decoupled from the combustion process. Means you can analyze the combustion process. Finally, then you can see the condition for the formation of thermal NO. And let's look at their simulation results. In 1971, Westenberg, they give us a correlation equations for the formation of the NO, and for fielding mixtures. Actually, they have a very good predictions. But some people found out there is some discrepancy between the major and the predicted NO formation rate in the combustion zone and also in the field-rich conditions. But the formula proposed by Westenberg in 1971 is very good for the predictions in the fielding mixtures. Why there is the discrepancy between when you use this equation, there is a discrepancy between major and predicted thermal NO, because in the combustion zone and also in the field-rich condition, there is some contribution coming from the plant NO. I will explain earlier. Okay. Now they have a good conclusion. They have a conclusion on that. Good predictions occur as a combustion takes place under lean and near stoichiometric fuel air conditions, which primarily they do not have the fuel bound nitrogen contribute, and the gaseous flame will free from the fuel NO contribution. Okay. And people always find that in diffusion flame NO formation, because I already mentioned the NO formation is achieved at the high temperature conditions, and they require nitrogen from the nitrogen atom from the nitrogen in the air, and oxygen atom from the oxygen in the air, which means that the nucleation or initiation for the thermal NO formation should be very close to the location, has high temperature, and has enough nitrogen and oxygen. Definitely, that region should be very closer to the fueling side of the reaction zone. Okay, they should not go to the rich side. Fuel rich, in that case, that you do not have too much oxygen and nitrogen in that side, even they have a higher temperature. Okay, and people and as we described earlier for the particulate formation, I mentioned for diffusion flame, the fuel side contains a lot of fuel, right? Then they can produce a carbon particle quickly, and near the temperature, a high temperature region, that means you can have a good formation of particulates, particle, carbon particle soot. But for the lean side, actually, this is a good regions for NO formation, because the temperature is high and you have enough nitrogen and oxygen from the air. Okay. Now this is some calculation and compare with the experiment. The left figure, the upper one, tell you there is the kinetic calculation for methane air reactions, and you can see along the horizontal axis represent the calculation time, and there is the different the more fractions for different species. You can see from this figure, you can estimate the flame position for this premise flame is around, based on the time scale, you can see the flame position maybe sits around 10 to minus 5, the power of minus 5. Since you can see initially the nitrogen or nitrogen content, I'm sorry. Nitrogen concentration is almost the same, is a large value, and the rest of the species has a small fraction compared with that for nitrogen. And you can see oxygen reduced. Okay, there is oxygen from the around 21%. Okay, drop down, and by this kinds of sharply drop, you can imagine there is a flame position here. Okay, there is a premise flame here. Therefore, you can see you can have some decomposition of methane to produce some intermediate species. But those intermediate species, for example, OHH and CO, they will be a complete convert to the products of carbon dioxide and water, which means that you can have the highest carbon dioxide around here, right? This is a CO2, and H2O is around here, H2O, okay? And you can look at all the variation on the species concentration to understand at this point, these positions, actually the combustion process almost finished. When they finish the chemical reactions, and then you find out the the production of nitric oxide NO start to increase. You can see they start to increase, which means the NO formation actually occurs in after the combustion process. Okay, this is an indication. And then right hand side, these figures tell you the open circles and the open triangle symbols represent the data from the experiment, and the solid line represent the calculation, and you will find out for the this is the mixture mixed with oxygen, nitrogen, and argon mixtures, and then they do the experiment under temperatures around very close to the 3000 K is high temperature. Okay, and you can see if you control the rich conditions, then you can see the NO formation increase very fast from the beginning, then go to very close to the equilibrium conditions. And from the calculation and in the equilibrium conditions, actually the value, the predicted value, is small than the experiment result. This is caused by the influence coming from the prompt NO, I will tell you. And for the lean one, you can see from the experiment and the calculation, you find out the NO concentration continuous increase, and they may go to the further downstream. Even go to the further downstream, they still lower than the equilibrium, the equilibrium data, the data in equilibrium state. Since that means that for the lean conditions, the temperature is not too strong, not too high. They will extend to a further long. They require a further residence time to complete the NO formations. Okay. And here there is some comparison by changing the equilibrium ratio of your mixtures of methane air. You will find out there is the flame zone here. After the flame zone, you start to have NO formation in the downstream of the chemical reaction zone. As I mentioned earlier, you need to finish the combustion process, and all the heat release and the mixture reach to the higher temperature. In this high temperature region, you still have a certain amount of oxygen and nitrogen, then they will have a chance to go through the NO formation process. For the lean case, actually, they do not have too much NO formation, thermal NO, but very close to the stoichiometry, or go to a little bit to the richer side, then the NO formation become very strong, very prompt. Here, especially for the equilibrium ratio to the 1.15, this represents the other contribution coming from the prompt NO. Now we go to the next category for the NO formation. We call this as a prompt NO. There is the two criterions for understanding on the formation of prompt NO. You need to understand they need to have a large concentration of oxygen atoms within the reaction zone, especially for the stoichiometry mixtures. As you remember, the formation of prompt NO, they have a go to the two step. The first step, they need to have some hydrocarbon radicals, for example, CH radicals or C2 radicals, and those radicals here. Here there is the two chemical formula you can follow. Initially, you need to have a CH radical and a C2 radical coming from the decomposition of your fuel. Then they need to meet with nitrogen. Okay, when they meet with nitrogen, and they will go through this reaction to produce HCN or CN. Okay, later on, HCN and CN will react with oxygen, which means the first part from the reactants, you understand they need to have a large amount of hydrocarbon radicals. Then the rich condition is good for the prompt NO, but they still need to have a certain amount of oxygen, okay, to react with the HCN and the CN in the product site. Okay, then you can look at the procedures for the prompt NO formation. This is a time scale represents the chemical reaction will go through this time variation. You can treat as the position of your premixtures. Okay, and there's the mole fractions for NO and HCN. From the zero, you find out we start you can treat as the position of your premix frame, very close to the in the upstream side. Okay, but initially you can see the hydrocarbon drop down very fast because the in the flame regions, they have a preheating zone, and you will have a decomposition of your fuel to change the original hydrocarbon fuel to the hydrocarbon radicals, include HCN and HC and C2. Okay, and later on, those HCH and C2 radicals will react with nitrogen to produce the so-called HCN or CN, right? Okay, those species contain certain amount of nitrogen atoms, and they will react with the rest of the oxygen radicals. Then they will convert HCN to NO. You can see initially the HCN increase very to the large value in the downstream of the flame zone. Okay, the hydrocarbon reduce its concentrations, but HCN increase. But later on, those HCN convert to NO. Therefore, NO will go to the maximum value. Then they will remain at a certain constant value. Since they have if you continuous convert HCN to the NO, sometimes there is a certain amount of NO will react with the HCN, and they will convert themselves to N2. Okay, and here they tell you the prime NO formation is absolute depend on the presence of hydrocarbons, especially the HC, the CH and C2 reticle. When you look at the CH and C2 reticles, basically you will find out there is no possibility to have a prime NO from the CO and the H2 flames. If you just have a H2 flame burning hydrogen, then you do not have a chance to have the carbon get involved, right? You do not have this intermediate radicals, then you do not have a possibility to produce HCN or CN. Similar way, there's if you burn a CO, then you will not have a so-called prime NO formation. Okay, and we from the calculation, and we find out they are independent on the residence time, and all the formation for the prime NO occurs in the fuel site for different kinds of fuel. You can see there is one for equilibrium ratio. Most of the fuel has a certain amount of prime NO occurs in the rich sites. Okay. Here, they conclude the maximum prime NO is reached on the fuel side or fuel rich side of stoichiometry, remain at a high level through a fuel region, then they drop sharply after equilibrium ratio of 1.4. Here you can see around 1.1 is not too rich, then you do not have you cannot produce the HCN enough. Okay, but for the 1.35 equilibrium ratio, they can produce, but separately they will drop down because those HCN will convert to the NO. Okay, this plot just tell you the variation of the HCN concentration. The decrease HCN means the increase in the prime NO. Okay, which means around the equilibrium ratio very close to the fuel rich sites. They can produce the big number of HCN, but later on those HCN will convert completely to the NO. But for equilibrium 1.1, as I mentioned, they are too close to the stoichiometry. They do not have enough hydrocarbon radicals released. Therefore, therefore, they do not have a good contribution on the HCN concentration, and follow they don't have NO prime NO formation. But for rich sites, you can see there is a big amount of HCN produced in the downstream sites, but they do not have a chance to convert it to the NO, because for HCN or CN they require the oxygen additionally to react with them to form the NO. This is the penalty for the fuel too rich. Then you may not have enough prime NO to be produced. there's you can see there's a drop down for different kinds of fuel in the very few rich sites. You can see, for example, for the ethylene, when the equilibrium ratio higher than 1.8 something here, the NO concentration drop down very fast. In this region, actually, they tell you they are lack of the oxygen concentration. Then the conclusion is that for equilibrium ratio of 1.5, a fuel-rich condition for which little prompt NO is found, the HCN continues rise and is not depleted, as I mentioned. Below an equilibrium ratio of 1.4, there are still sufficient oxygen radical present to react with HCN to deplete it, then to form the NO. That was emphasized by equilibrium ratio very close to the equilibrium ratio equal to 1.35. Okay. Final part for the NO, we talk about the fuel NO. Basically, those fuel NO coming from the different kinds of fossil fuel. In general, for a highly stable or distillated fuels, they will contain the 2.3 weight per second nitrogen content. And if you look at the average value of heavy distillates, then the weight percent will reduce and reduced up to the lower to the 0.65 for crude oil. Okay, and for the high distillate fuels means because under the distillation process, certain amount of light fuels already evaporate. Then the whole thing, the whole fuel contains the higher boiling point fuels, then the nitrogen content percentage will be increased. For most coals, they always contains a 1 to 2 in weight percentage. Okay, this is a general. We understand how much nitrogen will come from the fuel you used. And people understand, since those kinds of nitrogen mechanisms are quite complicated from different kinds of nitrogen containing fuels, but usually people understand if you have, for example, the left-hand side in all formulas represent the fuel, the nitrogen containing fuel, for example, NH or HCN, CN. HCN, CN, we just mentioned for the prompt NO, you may have HCN and CN radicals from the hydrocarbon radical react with nitrogen to produce. But for the fuel NO, actually they come from the fuel itself directly. Okay, and HCO, and then they will react with oxygen through this chemical formula. For example, HCN will react with oxygen atom to create to produce the NCO, and then NCO will again react with oxygen. Later on, they will produce the NO. By this possible chemical reaction, that finally they will produce the NO. Okay. But when you have those kinds of fuel NO, you should remember there is two very important chemical reactions. They are in competitions. Okay. Here, there is they tell you there is the two reactions. One is a reaction with oxygen-containing species to form NO. Those intermediate nitrogen intermediates will react with oxygens. Then they will produce. This is for the NO formation. But the other one, there is some reactions. Those nitrogen intermediates will react with not NO itself. When they react with NO itself, then the chemical reaction will go back to produce to return their original nitrogens. Okay, the reaction B tell you the separations on the formation of NO. Okay, and the reaction A can be described by this formula. Okay, the formation of NO from fuel N. Here there is the fuel N react with oxygen. Okay, and this is the production of NO through the fuel NO reaction. And the second one, they tell you the separation of the NO because the fuel N will react with NO, then they will let the nitrogen atom go back to the original nitrogen. Then this is a separation on the NO formation. That means the formation and the removal of NO by reactions, they are not involving the fuel nitrogen. Okay, I'm sorry. There is a several reactions, three or four. They may involve, but we do not mention here. But the major reactions will be controlled by the equation one and the equation two. And here, one thing we need to mention, since the NO formation and the combustion process occur on the similar time scale, because in the process you need to release the fuel N, and the fuel N should be the release of fuel N occurs in the combustion process. Then you need to assume the reaction involving the nitrogen containing species should be very fast. Then they were coupling with the combustion process easily to be go to the equilibrium state. Then here, usually the NOx from concentration exceeds calculated equilibrium value in the combustion zone, and in the post-flame of the NO concentration decrease relatively slow by the fuel-lean mixtures, and more rapidly for the fuel-rich mixtures, because you will convert a certain amount of NO, because those NO will react with the fuel N, and then the NO formation will be suppressed. Okay, here this give you some example. For example, here they choose the different kinds of fuel air equilibrium ratio and burning the brake oil by additional nitrogen in. You can see originally the mole fraction for NO basically is in this low level for the brake oil. But when you add more nitrogen in, you will find out the overall the NO fractions increase definitely, because you have additional fuel N into your the combustion process. But if you look at the equilibrium ratios, you will find out when you have a equilibrium ratio closer to the stoichiometric ratio, then the NO formation will be dropped down. Okay. Now there is some observation in the fuel-rich system. The combustions reaction of fuel nitrogen intermediate must be considered in doubt, mainly because the normal oxide species of O2, O atom, OH are present only in very small concentration. That means that in fuel-rich conditions, the conversion of fuel nitrogen into the fuel NO is less, and then you need to think about the reverse reaction of the fuel N react with NO, then overall the NOx formation will be reduced. Okay, this is another typical experiment. Burn the ethylene air flames for the A. This is the A case, and they try to do the experiment by adding the paradigm. Paradigm here is the hydrocarbon fuel contains a certain amount of nitrogen. Okay, and the curve A represent the no paradigm additions is a planar ethylene air flame. But from B to C, the percentage of paradigm will increase from 0.1 to 0.5. B to C, a continuous increase, then the NO concentration will be increased. But for the D, then we directly add the NO into the system. Okay, now you will figure out when we have a larger amount of paradigm at significant decay of nitrogen, nitro oxides is observed after the reaction zone. You can see they drop down. Okay, the horizontal axis represents the time scale. That means that when you go to the further downstream, the NO concentration reduced. Okay, and adding small amount of paradigm, little decay of NO occurs in the post regions. As I mentioned, B to C, we increased from the 0.1 to 0.5. At the curve C, actually they reach to the 0.5% paradigm. Okay. And an increase in higher paradigm additions result in high NO concentration leaving the chemical reaction zone, but this concentration drop appreciably in the post-flame gases to a value catalyst of flame, but well above the calculated equivalent value, still higher than the value estimate from the equilibrium conditions. This is the observation from the experiments. Now, we just introduced those kinds of NO source from the thermal NO, fuel NO, and the plant NO, and some physical parameters need to be considered. For example, here they tell you if you look at the temperature fluctuation, especially for the turbulent flame, and those instantaneous temperature level exceed the time average temperature level, then we will have some influence on the formation of the NO. Thomson in 1975, they give you the experimental result. If you have a fluctuation temperature around 100 K, then they will increase the NO year 150%. Okay, those kinds of fluctuations will increase the formation of the NO. Actually, from our experience, we try to use the flow recirculation to make all temperature more uniform inside the temperature flow field, and this is good for reduction on the NO formation. Okay. And there is a important conclusion for real application in gaseous hydrogen fuel. Okay, hydrocarbon flames, for example, the methane flames, and in engines burning higher distillate liquid fuel. That means that you already get rid out of the get rid out of those kinds the high boiling point fuels. Then the principal mechanism for NO formation is a thermal NO, because those gaseous hydrocarbon flames and high distillate liquid fuels, they do not contain too much of the fuel NO, the fuel end. Then mainly the NO formation coming from the thermal NO from described by Jadovich, a mechanism we described earlier. But for the furnace, if you burn the high heavy fuel oil or pulverized coal, they always contain certain amount of fuel N. Then the fuel NO mechanism is responsible for at least 80% of total NO. This is a basic understanding on the applications. Then we go to the nitrogen dioxide. Actually, the amount of nitrogen dioxide usually small compared with NO in exhaust gases. They can be formed in the combustion zone, followed by subsequent conversion of the NO2 back to the NO in the post-flame region. Finally, they in the downstream region, usually they will convert to the NO. Now let's look quickly to think about the techniques for controlling NO emissions. For example, the first one, we look at how to suppress the formation of thermal NO. Actually, you try to reduce the peak temperature level, as I mentioned. When the temperatures are maintained below 1800, that means more than the 2000 K, then the thermal NOx will not be appear. It should be at very low level. Now, how to make those kinds of temperature lower than 2000 K? People try to use a so-called stoichiometry, or we say the stage burning. That means that you need to burn this amount of fuel, but we try to separate with a different stage for complete combustion. For example, for this arrangement, the arrangement for these boilers, initially in the in the lower parts, we just supply the 85% of theoretic air into your boil. That means that in this regions, the burning will under the rich conditions. Okay, under rich condition, temperature will be suppressed, right? Then we go to the next. Since you have the burning in this region is rich conditions, you do not have enough oxygen to complete all the burning for the fuel. Then you need to, when those gases flow upward, you need to supply additional 50% of theoretical air required for combustion in the downstream side to make those kinds of excess fuel to be burnt. By this arrangement, uh, the lower portion relate to the rich burning. The upper part remain will show you the dim burning. Okay, now by this kind of arrangement, all the temperature will be controlled. All the temperature in this region will be controlled lower than the 2000 K. Okay, then then you may not have too much thermal NO be produced. This is a typical plot to tell you here. This is a percentage of furnace height represented by a horizontal axis from 0 to 100. Originally, if you just use the one stage, that means that you perfectly mix your fuel with the required air, then the temperature will decrease from the lower portion here from 0. Initially, you will have a very high temperature because the mixing is very good, very close to the stoichiometric ratio. Then they continually reduce when you go through from the lower portion to the upper one, because those heat will be absorbed by the circulation water. Okay, then the temperature will continuously reduce. This is for the single stage burning. Now, if you choose the two-stage combustions, by this the temperature variation will be changed to this time. Initially, since the first stage is under rich conditions, then the temperature should be lower than the previous one. This is a small temperature variation. At this point, then you apply additional 50% theoretical air in this region. Then they start to have a dim mixing, increase the temperature in your combustion chamber up to the optimal the high value. Then they will drop down continuously. Okay. Now the third case, actually they try to use the so-called flue gas recirculation get involved. They can additionally give you good conditions for on temperature variation for the NO formation to suppress the NO formation. Here you can control the temperature, average temperature even lower compared with the first case. What is the flue gas recirculation? Then is the next step we need to mention here. Here, sometimes people will bring certain amount of flue gas from the flue gas steam and make it back and flow into your combustion zone. And since the flue gas, they do not contain too much oxygen and the temperature is high, okay, but they can they just like the high temperature inert. When they put into your combustion chamber, actually they can help to try to control the combustion temperatures, and they will give you the very effective and on the NOx formations. And this flue gas recirculation is a good measure to reduce the flame temperature, but you need to have a arrangement for the recirculating the flue gas back into your combustion chamber. For the fuel end or the most efficient way to reduce the formation on fuel end oil is you try to rearrange the the supply of fuel and try to increase their residence time. Sufficient time is very important for the separation of fuel and oil. Try to convert all the fuel and oil for all the fuel N radicals, and they will produce they will release the NO, and NO will react with a few N, then they will convert back to the N2 as I mentioned earlier. For example, there is the different application where for given boil, you can different you have a different design for burning your pulverized coal. The first one we call this is a front fire. This is a very usual way to burn the pulverized coal. You put the old nozzle just impinging out in the same directions. Sometimes it's usually it's a horizontal. Okay, and then there is a black zone represent the burning zones. Okay, and then you will see there is a combustion region shown by these dark regions. Now you may try to use the other way, is a so-called horizontal opposed jet fire. Then let the injectors coming from the different direction, they were impinging together. When they impinging together, actually they will reduce their own momentums, and to make all the flow below this small, then they will increase the residence times. And this is another one. And additional one is a so-called modified opposed fire. Actually, they try to change their angle of injection to downward. That means the flow will move first to the lower portion, then they will convert to the upper regions. By this kind of arrangement, we try to look at the NO emissions and to show you how the variations on the NO formation here. You look at for the front fire, the first case, actually the NO formation depend and vary with the burning rate. Okay, they are quite high. It's increase with the heat release, and they are in these high regions. Okay, but when you change the fire style to the opposed fire, the second case, actually the NO formations curve will be reduced compared with the previous two cases. And if you use additional modified opposite jet fire, the NO formation even reduce further. Okay, you can see this kinds of arrangement on your fire structures. Then try to increase your flow time, residence times. Then you will make those few N complete convert to the NO, and then react as possibility to react with NO, then they go back to the original N2. And for the prompt NO, actually, as we remember, the most important thing you try to burn the condition under very rich conditions. Then in this situation, you do not have enough oxygen. Then they cannot convert the HCN or CN back to the NO. Then you will have a smaller NO prompt NO formation, or you try to burn the this is a very similar to the stage combustion. Initially, you burn the rich condition, then you go back to the lean combustion. Okay. Now, yeah, I think we end up with these slides.